Alright people, today we're going to go to 5.4 and in a broad sense of things, 5.4 is really about electromagnetism, right? It's not just magnetism, it's about electromagnetism. Now EM, if you look at it, it is how electricity creates magnetic field, and I will go a little bit more into this when we are finished with our syllabus, the whole thing. But I'll just give you one statement that may just be a little bit unsettling for you. Actually, magnetic field doesn't exist. It doesn't really exist. It is actually a byproduct of electric field. It is the distortion of electric field. In fact, if you go deeper, it is the relativistic effect. That's what Einstein was talking about many years back. It is actually the relativistic effect of electric field. That's why if you think carefully about this, is there a case where you have magnetic field without moving charges? You need to have moving charges, right? Current, you need to have moving charges. Even in the magnets, you have electrons spinning around, so you need to have moving charges. It is actually an electric field effect. But we'll talk about this in the future when we have time and when you finish your IOC and everything. Okay? So creates magnetic field, and magnetic field, how magnetic field interacts with electricity. So this is basically EM. That's it. We'll go through the first half at least on the left, and then if we have time, we will be able to go through the second half on the right. I think we have time, but let's see how we do. So let's go through the basics. Current, you have done this before. It goes like this, and like this. There are three things I look out for. The shape, which is circular. The spacing, which should get further and further apart. Someone tell me, what does the increasing space between the field lines mean? It means that the field strength is getting weaker and weaker. It gets stronger and stronger as you go into. Yes, Shannon, that's what you say, right? Yeah, you're saying that it's getting stronger and stronger as it goes in. You're not wrong as well. So, how about direction? Still remember your right hand grip rule? Yep. So, in the context of a current, the thumb represents the current or the field? Current, yes, correct. So, your thumb points here and the field goes here. Everything looks okay until I give you a 3D diagram and then you have to imagine. We'll come to that, so no worries. So for a single wire, it goes like this. How about two wires? So say for example, if you get a wire that goes like this and like this, current going, people, cross means what? Current goes in, yes, correct. And then dot means out, okay? Now, still remember how to draw the field pattern due to two currents? Have you been taught in secondary school? Yeah, it looks like a peanut, yes, correct. It may look like those kind of Japanese ninja, depending on how you look at it. So it looks like this. Now something interesting will happen if you go further and further away. Can you see that as you go further and further away, it looks more and more circular? It looks more and more circular, which makes sense. Because if you have two currents close together and they're moving in the same direction, it makes sense that as you go very far away from them, it looks like one. Right? So it looks like one current. That's why as you go further and further away, it begins to look more and more like a circular field. Okay? Like one wire. And there's another thing that's interesting for the field over here. There's one point at the center where there is no field. Why? Because if we call this A and this B, the field due to A over here will be pointing down. And the field pointing up will be the field due to B. If you use a right hand grip rule. It is. Now the fact that BA and BB can cancel out each other, what does it tell you about the nature of magnetic field? Is it a vector or scalar? Vector, exactly. It is a vector. Okay? So it is a vector quantity, you must remember this, and I'll explain to you why is it a vector quantity. There's a definition to magnetic field strength. Much like a definition of electric field strength, there is a definition, and gravitational field strength. The reason why I say that it looks like a Japanese ninja is because if you add this and then you do this, it really looks like a person. Right, it does look like a face, right? That's kind of, okay, fine. I'm just imagining things. Come on, people, can you be a little bit more creative? Okay, the next one is, what about field due to two wires with current in opposite direction? At the center, do the field cancel off or do the field add up? Add up, exactly. So the field at the center over here, due to this wire A, will be still pointing down. And the field over here due to B points down as well. So it will be a very strong field over here pointing down. And it looks like this. It will look like this. Okay? And Balaji, I think what I'm showing over here is more interesting than your tie. Thank you. Yeah. You can put it on. Yeah, actually you don't have a choice. Put it on. Cool, so 2 fields, 2 wires and 1 wire. Now what if you have 4 wires? Now use your right hand grip rule for each of the wire and find out what's the direction of the field due to the 4 wires at the center. Enjoy. Remember that it is a vector sum. We got 1, 2, now we got 4. 4 times the fun. Okay. Anyone else? Anyone? Okay, let your friends answer. Let them try. Can I have someone who hasn't spoken for a long time? Joseph, I want to hear a voice. Oh, what's that sound? Were you making a sound or were you giving an answer? But this thing is the direction of the field. No worries. There are only 10 people here. If you get it wrong, only 9 people will laugh at you. It's okay. Sorry? Cancel each other. So your answer is no field, yeah? So let's do it one by one and see whether it is no field. So let's call them A, B, C, D. The field due to A at this point over here, how do you know the direction? Very simple. If you can see it, it's good for you. But if you can't, this is one way to help you. Draw a dotted line over here to the point. The field will definitely have to be perpendicular to that dotted line. Agree? Because if it is a circle, if the current is here and if it is a field is always a circle, if you draw any line to any dot over here, it will be perpendicular to the direction of the field. Right? So first of all, you draw a dotted line to the point and the field will definitely be here. Then you use your right hand grip rule. In and it goes southwest. Okay. Now if you do everything following this rule, you'll find that 2 of them points here and 2 of them points here. And therefore, the field points here. Now there is an easier way. And I purposely didn't want to give you the easier way because you have to go through the hard way so they appreciate the easier way. Remember that for a coil, can you see that this is a coil? Can you see it's a coil? Yeah, once you see it's a coil, it becomes very simple already. You use the right hand grip rule with the fingers as the current, so the field points this way. Okay? Cool? Yeah. Yeah. So the wires building up to that was a decoy. Cool, so that's more or less what you need to know. I wanted to go through this ASP component of like what's the expression. I was waiting for one of you to ask me, what is the expression for the magnetic field? Remember for electric field I give you F equals to KQ upon R square, gravitational GMM upon R square, but I have up till now not given you the expression. Now just for your interest, I will show you how to use it when we have time in the future. The expression for magnetic field is this, for a wire. This is due to a wire. Now what are the symbols? Mu naught is what we call the permeability of free space. It has the units equals to 4 pi times 10 to the power minus 7. I obviously is the current, 2 pi. R is the distance of the current from the point. So if I got this point and this is 5 centimeters, I'll substitute 0.05 into here for the R. So that's the expression for the field strength due to a current. Okay. This is the only field, if you notice, out of G field, E field and B field, it is actually the only one that is not 1 upon R square. It is the odd one out, if you notice. Yeah, it is the odd one out. Now before I go on to the, or probably should I go on? Yeah, I think it's time for us to go on to the definition of magnetic field.
By R square, you mean 4 pi R square?
No, this one, yeah. For electric field and magnetic field, it's 1 upon R square, proportional to 1 upon R square.
Yeah, so but exactly sphere 4 pi R square.
Yeah, I'm not talking about a sphere, but I'm just saying that the relationship of the field to the R, it's 1 upon R. Yeah, that's all I'm saying. I'm not talking about a constant. Cool. So let's go on to the force. You have learned this before. When a current interacts with a magnetic field, a force appears, and when we talk about force, there are 2 things that we talk about because it is a magnitude. It is a vector quantity, so we always talk about direction and magnitude. All right, let's talk about direction first, something you have learned before. Do you remember this? I don't know what your teachers have taught you in secondary school. Your teacher may have taught you father, mother, child. Father for force, mother for magnetic field, child for current. I don't know why this works for some. Some people may have other ways. So some people say FBI. Yeah, FBI, yeah. So some people may, those more pastoral kind will probably remember father, mother, child better. Yeah? Those people who like action kind of things, probably FBI works better. So whatever it is, so as long as you remember this is force, magnetic field, current. So can you use the left-hand rule, Fleming's left-hand rule, and tell me what's the direction of the force? This gets a little bit distracting. You do know the 6 direction, right? Left, right, up, down, in, out, just in case the 6 directions, yeah. Up, down, left, right, in, out. The in, out and the up, down tends to be a little bit confusing. But for some people, all confusing. No sense of direction kind. Especially when you drive a car in reverse, left becomes right, right becomes left. Yeah, right? When you reversed. Or when you play remote control cars, when the car is coming towards you, left becomes right, right becomes left. Okay, so the direction is up. Yes, correct. Now, let me caution you, because some of you may actually have learned right-hand rule, Fleming's right-hand rule. Some of you may have been taught, or some of you may have been taught by some sources, need not be teachers, should not be teachers, that left-hand rule is used to find force. Right-hand rule is used to find current. Any of you heard of this statement before? Left-hand rule is used to find force, right-hand rule is used to find current. Wrong, It is a very dangerously wrong statement to remember. Let me show you why. Let me give you an example. So, I have a current flowing in the wire such that it produces a force into the page. Find the direction of the current. Do you use the right-hand rule or the left-hand rule? You're finding current. Do you use right-hand rule or left-hand rule? Listen to the context carefully. The current flows in the wire, interacting with the field, creating a force into the page. Do you use a right-hand rule or left-hand rule? Left, because the context is a current interacts with a field to create a force. You use a right-hand rule when you move a conductor in a magnetic field to induce an EMF. It is different. So I purposely set the question in such a way where you find the current, but you actually use a left-hand rule. So the way you discern whether to use left-hand rule or right-hand rule, in fact, I don't advocate for right-hand rule, but if you are confused, the way to discern is always whenever a force is induced, you use left-hand rule, regardless of what you want to find. When a force is induced, meaning that you have a force due to the current interacting with the field. Whenever you have an EMF induced, you use the right-hand rule, regardless. Okay? So that's very clear. What is induced? Cool? Okay? Now, let me ask you to try another 2 examples using left-hand rule, and then you tell me what are the forces. This becomes a little bit more difficult now. The top and the bottom example. B is magnetic field. Why B magnetic field and not M? I think it's to probably honor this person called Biot. He came up with some really fundamental magnetic laws. So that's probably why we use B to remember this person called Biot. Biot. Yeah. Have you heard of this law called Biot-Savart's law? Okay. There's this law by Biot. So probably that's where the B comes from. First one, anyone? How? Left-hand rule always perpendicular one, So how do you deal with non-perpendicular situation? Left-hand rule becomes the version 2 left-hand rule. Version 2 left-hand rule. Like this. So the way to go about this is magnetic field is a vector quantity, right? So you resolve it B perpendicular and B parallel. And you always use the perpendicular component. One of the very important things about magnetic field is think perpendicular. Always perpendicular. Everything must be perpendicular to every other thing. All right, we'll touch more about this when we do EMI next year. So how do you point your finger? The B should be pointing this way, the current pointing there, so the force is inwards. So the B should point this way. The current should point this way. Yeah, so it points in. Now, one of the way to handle the situation where if your hand is almost at the point of fracture, when you twist it so much that it's at the point of fracture, you can always reverse one of them. And then just remember to reverse the force. Yeah, let me show you how. So say for example, if you find that the field pointing this way and the current pointing that way is a little bit too difficult, right? So I point the current this way. So the force is out, right? Easier on my hand, very easy on my hand. So I point the current this way, which is opposite to the actual current, and the field points this way, the force is out. So I just need to reverse the force. Just remember to reverse the force. Yes? Okay. Excellent question, Shannon. Excellent question. The reason why I intentionally not resolve current because current is a scalar. I don't want to send home the wrong idea. Yeah. But you'll get the correct answer as well. Yeah, you'll get the correct answer as well. So I was very careful not to resolve current because current is not a vector. Force, field is a vector. Cool. Now we haven't touched on the equation yet. We touched on the direction, but can you see that there's a component part that comes in? It's not just the field strength, it's not just current, it's not just length, it has to do with the orientation as well. And this is, we'll sum it up. Can you tell me what's the direction of the force for this one? I said think perpendicular, right? So is there any field perpendicular to the current? No, yes, correct. Force equals to 0. So the force depends on orientation, and that's why the force is equals to BIL sine theta. The angle sine theta, if you want to interpret it this way, it's B sine theta times IL. Now what is this B sine theta times IL? If I define this angle theta as the angle theta between the current and the field, can you see that this is 90 and therefore this is 90 minus theta, therefore this is theta. Okay, this is 90 minus theta. Now if I were to pull this field out, this is the B, this is the B perpendicular, this is 90 minus theta, this is your B, this is the right angle. Can you see that B perpendicular is equals to B cos 90 minus theta, which is B sine theta. So the sine theta is there to account for the perpendicular component of the field. That's the reason why the theta is there. All right? So you must understand the physical meaning of the theta. The reason why I want you to remember the physical meaning of the theta is because if Terence Chiu were to set the question, I would definitely be nasty and give you this as angle theta. Then the equation becomes cos theta. So if those hardworking students who actually die hard remember equations and then just hum-tum any angle that you see in the question, then you will get tricked. Yeah? You may see it as a careless mistake. You say, oh, it's a careless mistake. Actually, it's not a careless mistake, it's a conceptual problem. Because you anyhow just get the theta and put it in without understanding what it means. Okay? So be very clear why you choose certain angles. And what's the meaning of the angle over there? Have you learned cross product? You've learned mathematical cross product, right? Wow, that's excellent, man. So we talk about the field in, right? So actually, this is F I L cross B. The B vector is very clear. B vector is the B vector here. So what is the L vector? L vector is the vector that points along the wire. So which direction does it point? Does it point along this direction or this direction? So you take the L vector as the direction of the current. So why don't we put it as the I vector? Cannot, because I is a scalar quantity, whereas length is a vector quantity. Displacement is a vector quantity. So how does this take into consideration? How does this gel with the Fleming-Stefan rule? Right? Using Fleming-Stefan rule, we deduce that the direction of the force is in. So if you use L cross B, the force is in. So this is what some people call the right-hand slap rule. Yeah? Right-hand slap rule. And it works. L cross B. It works as well. Yeah. L cross B. In. Don't believe? Let's try another situation. Current over here, field this way. Use your left-hand rule or use your right-hand slap rule. The current is pointing here, the field is pointing here, the force is down. Use your left-hand rule, It's down. You'll be correct. Go align your palm in the direction of the current and then slap the hand, the palm, to the field. Orientate your fingers, your palm, so that you can slap it to the field. It'll be pointing down. Use your left hand rule, it's also down. Yes, correct. Correct. This is faster. Yeah. But when you write the explanation, Fleming's left hand rule. Don't say Terence Chiu right hand slap rule, you will be slapped. Okay, so please write the, yeah. So, but if you feel that this is easier for you, or you, up to you. But mathematically, this is the equation. Cool. Right, let's try some questions, shall we? From easy to more difficult ones. Or what I think is easy. Let's go for the first one. This is ground. This is field. In. The field strength is 215 millitesla. The mass per length is equals to 0.05 grams per cm. Find the direction of the current and the magnitude of the current so that the wire levitates. The wire floats. Now, when you see the word levitate, what does it tell you about the magnitude of the weight and the magnetic force? They must be, come on, if it floats. It must be equal, yes, correct. And what do you deduce is the direction of the magnetic force? Up, exactly. So by doing this, you should be able to deduce the direction. You know that the force must be up, you know that the field is in, the current must be towards the. You'd be surprised that at this point, some students can tell you the wire is here, then what's the direction of the current? Out of the page. Dun, 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 dun. How is that possible? A wire is like this. Even if you tikam, it'll be left or right, right? Seriously, if you tikam, it'll be left or right. How can it be out of the page? So, left or right, people? Okay, the field is in, the force is up, so it's this way. Okay? Right hand slap rule. The force is up, you want to slap the current to the field is this way, so current slap the field. So the current must be this way. The current slap to field. Yeah. Right hand now, not left hand now. Don't use the left hand to slap. Oh. The right hand is the right hand to slap. Yeah. Okay, so the direction of the current is towards the right. Now you do the direction, the magnitude of the current. I'll give you about 3 minutes. Struggle a bit, and then I'll show you the answer. You're supposed to find the magnitude of the current so that the wire levitates, given the magnitude of the field and given the mass per unit length. By now you realize that I'll talk a little bit more about the definition of B later, after this one. But let's use the equation first. This is the week that we see each other every week, right? Every day, right?
Yes, sir.
Ah. Again? How long is the wire? That's a very good question. Do you agree that if you can levitate 1 centimeter of the wire, you'll be able to levitate every centimeters of the wire? If you're able to levitate 1 meter of the wire, you'll be able to levitate every meters of the wire. So you can let it be 1 cm, 1 meter, or up to you. You choose. But there is a method that you don't even need to find the length of the wire. Like BIL equals to mg, so I is equals to m upon L times g times 1 upon b. Do you know mass per unit length? You do. Be very careful at this point of time. I purposely give it to you in grams per cm. So you have to convert to kg per meter. Yeah, be very careful about this. I purposely give you in grams per cm, double conversion. Grams to kg is seldom a problem. It's always the per cm to per meter. You times 100 or divide by 100? Per cm to per meter, times 100 or divide by 100? Huh? Huh? If you got 1 grams per cm cube, you want to convert to grams per meter cube, do you divide by 10 to the power 6 or times 10 to the power 6? Times, yes, correct. Times. Because in 1 cm you have this, in 1 meter you should have more. Okay. Yeah, 10 to the power minus 3, correct. That's milli. Milli, centi, milli. What's the next one? Micro, nano, pico, femto, etto, iocto, zocto. Yeah, I think that's the smallest rate here, zocto. Yeah, your magic wallet. Yeah, there's all the answers inside. Yeah, the magic wallet. Okay. This year, year 6, the average grade for the class is a 7, I think. The common test, yeah, ASP. I think it's a happy occasion. I mean, yeah, they work really hard for it. I'm not happy because they all get 7. I'm happy because they work hard and they reap the fruits of their labor. Yeah, they reap the fruits of their labor. Tomorrow. The details of the results will be tomorrow. I can't tell you more. We're not supposed to, but sorry? They don't know their detailed results yet. Yeah. Sorry? No lah, hold their joy later lah, till later. Hold their joy. They're very hardworking people, they're very nice people. Yeah. Yeah. But it's a small class. It's a small class. Yeah? It's a small class. So no discredit to bigger classes where not everyone gets 7. 10. 10 as well. ASP. Yeah. ASP 10 as well. Okay, let's you work out the numbers, you will get the number. Can? So that's it. Now I mentioned about the definition of magnetic field. So what is this Tesla thing? By the way, do you know this person called Nikola Tesla? Yeah. He's the first person, I think, if I'm not wrong, he's the first person who came up with the idea of the remote control. Yeah, remote control. Yeah, remotely controlling or triggering things. Yeah, he's the first person who came out with a DC motor. But unfortunately, he's not a person who does marketing very well. So he lost out to Thomas Edison in many situations not because of he has no brain, but he doesn't have the gift of gab. Yeah, he doesn't have that business sense. In fact, Thomas Edison wasn't the first person to invent the light bulb. He was the first person to come up with an electrical system that allowed light bulbs to be used on an extensive scale. So people thought that he's the person who invented light bulb. Yeah. Okay, let's go. B is equals to F upon IL sine theta. In case you think that F equals to BIL sine theta came first, no, this is the one that came first. This is the defining equation for magnetic field strength. So how do we define 1 Tesla? So 1 Tesla is which is the units for magnetic field strength, is the magnetic field where 1 meter of conductor with 1 ampere current experiences a 1 Newton force when it is perpendicular to the field. So this is what they define to be 1 Tesla. And this is a very important thing. This defines how we quantify a value called magnetic field strength. Where 1 meter of conductor with 1 ampere current experiences a 1 Newton force when it is perpendicular to the field. Yeah. But if it is not 1 Tesla, if they ask you to define magnetic field strength, then you just need to say that it is defined as the force per unit current per unit length of a conductor perpendicular to the field. Okay? So just per unit per unit. How does it feel to have a unit's name after you? I mean, seriously, it's something. It's up till now, if I'm not wrong, correct me if I'm wrong, there's no Chinese units. There's no like 1 ren, 1 tan, 1 lim. Yeah, one ton. Yeah, 1 ton. There's no. There's no 1 ton. Come on, ha 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 ha. There's no such units, right? One chew. No, not yet. Not yet. Yeah. So probably one day in the future, there'll be one, yeah, one whatever lah. 1 coin. 1 coin. Yeah, that'll be really cool. 1 coin, 1 num. All right, I think that's time, and it's good time to stop as well because we just finished the conductor part. Next lesson, we'll go into the BQV, which is charged particle moving, and we'll talk about how it goes